Hi, welcome back to my YouTube channel. In today's video, we are going to learn how to sketch a graph of a quadratic function. Now, in this particular problem, we have some series of problems or questions that we need to be able to answer in order to properly answer this problem, in order to properly sketch the graph of this function using all the tools that are available to us through linear transformation. Okay, so let's just get right into the problem. So first of all, we have this function that we need to, so we have that function and we need to sketch this particular function, right? Now, it happens that in calculus, we fairly understand how to sketch certain types of functions, but not of this type. This type is actually very difficult to sketch. And it just so happens that these tools in linear transformation can help us to simplify this problem into a much easier problem to handle, right? So that's exactly what we're going to do. We're going to shift from XY coordinate to a new coordinate UV, right? And then we sketch the graph. So we transform this function into a function instead of a function of XY. We transform this into, so we call this phi in one way or another. So instead of a function of xy, we turn it into a function of what? UV. And then we sketch this one, which once we sketch this inadvertently tells us that what this is the sketch of the same function. And this is the idea we're going to use in this particular problem. So let's just get right into it. Okay, so what's the first thing? So the first thing is that we need to declare the quadratic part of this function. So we say a function is quadratic if each term of the function is quadratic. It has it has degree of 2. So when we look at this function, we notice that what this has degree of 2, which means, what I mean by degree, I mean the power of the variables. When you add the power of the variables together, so each term should have a degree of 2. So this has degree of 2. This also has degree of 2, which is 1 plus 1. So when you add the powers of x and y, you would have 2. Also here it has degree of 2. So but this has degree of 0. So the only quadratic part of this function, which we call phi of xy, would be 5x squared minus 8xy plus 5y squared. Now, this answers the first part of this problem. Now, what is next? The next thing is we need to rewrite this from this phi of xy. We need to write in such a way that what we can determine what we call a self-adjoint transformation from it. Now, notice that since this function is quadratic, what can we do? We can write it as the product of this vector xy with a matrix here. We'll talk about the entries of this matrix in a bit, and then the same vector xy. Now we need to determine what must be inside this inside this matrix for overall multiplication of these three items to give us the left hand side, okay, to give us this. Now, how do we determine that? Notice that in this matrix, what we'll basically note is here will be x, we have y here, we have x here, we have y here. So this entry will determine the xx, x times x, which will be x squared. This last one will determine y squared. This place will determine xy, and this place will also determine yx, which is same as xy. So what we'll do is, so we'll look at the coefficient of x squared here, which is 5. So we'll bring it to be the entry for xx. Now, the same thing for y squared, we'll put 5 here. Okay. Now for xy, we have only one term here, minus 8xy. We have to divide it equally on for both sides, because here it is determined by xy and here is also xy. So we just have minus 8 divided by 2, we have minus 4 here. And the same thing here, we have minus 4 here. So now when you multiply this vector with the matrix with this also vector, we'll get the left-hand side. Cool. And this is the trick we use from all the problems that has to do with quadratic functions. Now that we have this, now we can now look at this part. of this multiplication. So let me just use a different. So we can um, look at this part of this multiplication and call this t of what? Xy, which is the transformation we are talking about, right? So remember that I mean, in our so at this juncture, I'll just like to tell you that if you haven't watched the previous videos in this linear transformation series, make sure you do watch it, because there I did explain how we can look at a transformation through the lens of a matrix, right? So, and that's exactly what we're going to do with this particular problem. We look at this as a transformation where the matrix of transformation relative to standard orthonormal basis. So here we can now define our transformation. Remember, it has to be from R square to R square, right? Because you have 2 by 2 matrix. Where the matrix of transformation relative, where this is the matrix of transformation relative to standard orthonormal basis for R square. And what is this orthonormal basis we're talking about? We're talking about the standard basis, which is E1, E2. Basically, we're talking about 1, 0, 0, 1. So this is how we're defining the metrics based off of this quadratic function, and it makes sense, right? Now notice that what this transformation is self-adjoint, which is what the question was alluding to. It's self-adjoint. Why is it self-adjoint? Because the matrix A is symmetric, right? It is a symmetric matrix, which means A is equal to A transpose. Because, so let's just write it, because A is symmetric, and that's because A is equal to A transpose. All right. So T is self-adjoint. So we found the transformation. Now, what happens is, basically, let's back up a little bit. So we can see the quadratic function of x and y, and we see that what it can be written in terms of the multiplication of a matrix with a vector and the same vector. Okay. Now, what is fascinating is we just explained that this version of things is complicated. It's hard to sketch this version of things. Now, because we understood how to diagonalize a matrix, and we also know that a self-adjoint transformation is diagonalizable, right? Because of spectral theorem, and this was mentioned in previous videos. The link is down in the description. Make sure you do go through the rest of the videos to have a ground understanding of this. So by spectral theorem, we did say that if T, so we did say that if T is self-adjoint, then it implies that what? T is diagonalizable. So therefore, we're just going to diagonalize this so that we obtain a new matrix of transformation for this same transformation, and relative to what? A new set of bases, which will be called the orthonormal eigenvectors, and where the diagonals of the new matrix would be the eigenvalues. So let's just go ahead and do that. So this is the next part of the problem. We are going to diagonalize this. And in order to diagonalize, the first thing we need to find the characteristic polynomial, which is this. And this is defined as what? The determinant of what? A minus Ti. So basically the matrix that we have before, we need to minus T from the diagonals of that. So this would give us 5 minus T minus 4 minus 4, 5 minus T. So we need to find the diagonal of the determinant of this. And this is basically when you multiply this diagonal minus this diagonal. So that will be 5 minus T times 5 minus T, then minus 4 times minus 4. Okay, so this gives us 5 minus T squared minus 16. Now, when you expand this, this is going to give us 25 minus 10T plus T squared minus 16. And simplifying this further would give us T squared minus 10T plus 9, I believe, right? So from here, we need to factorize this, and we should know how to do quadratic factorization, quadratic expression factorization. So this gives us t minus 9, t minus 1. Okay. Now that we have this is the characteristic polynomial, we can use this to get the eigenvalues. So what would be the eigenvalues? Would be the root of this quadratic, of this basically characteristic polynomial. So this gives us t minus 9, t minus 1 equal to 0, which implies that what t must be equal to 1 and 9. So these are the eigenvalues. Now, from these eigenvalues, what we're going to do next? So let's back up here. So from these eigenvalues, we are going to determine the solution to the the solution to the eigenspaces corresponding to each eigenvalue. So let's start with t equal to 1, right? We have two of them. Now, when t is 1, we need to substitute t into this. So where is that? Into this particular matrix. So when t is 1, we have 5 minus 1, which is 4. We have minus 4 here. We have minus 4 here. 5 minus 1, we have 4 as well. Okay. Now, from here, what does this mean? We need to now, so this is the coefficient matrix of a homogeneous system. So what it means is, if this are variables, then we have 4x minus 4y equal to 0. And the second equation will be minus 4x plus 4y equal to 0. Both of them are the same equation, right? Just when you divide, the second equation is just the negative of the first equation, basically. So it just tells us that what we can just choose one of them and solve. So when you solve this, this means 4x must be equal to 4y, and then x is equal to y. So that means the solution system is just, they are the same, right? Now we can take x out, which will give us this vector 1, 1, right? And so it means that for the eigenvalue of 1, it will be spanned by this vector 1, 1, okay? So this is the spanning vector corresponding to the first eigenvalue. But then we are looking for orthonormal vectors, which means we are looking for unit vector. So what we'll do is, in order to get a corresponding unit vector to this, the corresponding unit vector would be what? When we divide this by the length of that vector, okay? So which will give us 1 over root 2, 1 over root 2. So this will be the first vector for our principal axis. Okay. Now, now that we have this, we need to do the second one when t is equal to 9. So when t is equal to 9, substitute into this again, into this matrix. Then that will be 5 minus 9, that will be minus 4. Then we have minus 4 here, then minus 4 here, then 5 minus 9 again, minus 4. So basically, this would give us minus 4x minus 4y equal to 0. We have the same thing, the same equation in the second row, right? So this gives us, we can just use one of them. So it means minus 4x minus 4y equal to 0, which means 4x equal to minus 4y, which means x is equal to minus y. Now, what does that give us? The solution set would give us x is minus y, and we have y here. So we can take y out, that will be minus 1, 1. So therefore, this particular eigenvalue is spanned, the space for this particular eigenvalue is spanned by this vector minus 1, 1. Okay. Now we need to again orthonormalize this vector, which means we have to so let's say this is u1, u2. We have to what? Divide this by the length of this. So of that vector minus 1 square plus 1 square. So which will still give us minus 1 over root 2, 1 over root 2. Okay, right. So these are the two vectors. And these vectors are called what? The eigenvectors, right? Or the orthonormal eigenvectors. So now we can conclude our transformation T. So the matrix of transformation in this case would be the diagonal matrix, where we have the first eigenvalue here and the second eigenvalue here as a diagonal matrix. The rest will be zero, with the eigen vectors. So with orthonormal, so let's write orthonormal eigenvectors, where the first one is 1 over root 2, 1 over root 2, and the second one is minus 1 over root 2, 1 over root 2. Now this tells us this is called the principal axis. So this answers the other problem. This is the principal axis for the new coordinate system. Now let's rewrite the quadratic function again in terms of this new information. So basically what we have so far is t. We are changing the matrix of transformation for t. T is the transformation from r squared to r squared, where the matrix of transformation relative to this new set of bases would be what? 1009 relative to the orthonormal basis. This thing that we got. Okay, this is what it means. So we just basically changed the way we look at the transformation, giving it a new matrix as well as the as a new basis for the transformation for both the domain and the range of this transformation. Now, what does that mean? Now, usually before we have this quadratic function in terms of xy, which was written in this form. Don't forget this. This was 5. I think this was -4, 5. Now we are rewriting this. Instead of using this for our matrix of for the transformation t, we've changed it into a new coordinate. So the transformation is now this one. So in terms of uv, the matrix of transformation will now be different, will now be the diagonal one with the same vector. So we've just switched things around. By instead of working with xy coordinates, we have changed it to what? uv coordinate, where this would be the new matrix for this transformation. Okay, nice. Now that we have this, when you multiply this thing out, it turns out that what is just, don't forget, just the same way we did the other time. I mean, when we started this problem. So this will be the coefficient of u square. So this will be 1 u square, and this will be the coefficient of v square plus 9 v square. So basically, so we have transformed the function from phi of xy to what? Phi of what? uv. And this will be the new thing that we're working with in the new coordinates. Coordinate uv would have the same quadratic function has now been turned to this. Now, what does this mean? Remember that initially we had this quadratic function equal to, so let's just go get back up. We had this quadratic function to be equal to 9, right? Don't forget, to be equal to 9. So which means this new function, phi of uv, will now be equal to 9. This is what we need to sketch. So the question turns to what? Sketch this, which was the bigger picture I explained earlier on. Sketch this. Right? Now, remember that the coordinate system has now been changed. Now, let's see how to sketch this function. Now, so let's take a look at that. So let's look at take a look at this. Okay. So all right. So this is the original coordinate xy that we are supposed to sketch this this function, but we know that we couldn't sketch it in this coordinate. So now we are switching to UV coordinate system. Now the first thing is that we need to understand that this new coordinate is just a way, it's just a coordinate. So this UV coordinate in relation to this xy, it is somewhere on this plane, right? On this xy plane. Now notice that we would have to rotate this xy coordinate a little bit, right? So how do we know we have to rotate it? Now, don't forget that you got a new coordinate. What helps you to determine the new coordinate, which are called the principal axis, that will determine which are the agent vectors. Don't forget that this is right. Don't forget this. Now, in the old coordinate system xy, the vectors guiding this coordinate system, as you can tell, is e1, e2, which is this vector 1 0 and 1 0 1. And now and these are the same vectors that we used. So remember, those are the vectors that we used in this particular force transformation. We said this was the matrix of transformation relative to these standard bases e1 and e2. Don't forget that was the reason. So so this means that what this coordinate is e1, as you can tell, when x is 1, y is 0. So this coordinate is guided by this e1, and this coordinate is guided by what? E2. Now we have completely changed e1 and e2 now to this new coordinate. So this is the new coordinate f1 and f2 that will determine the vectors in the new coordinate system uv. Okay, so now we need to know where does f1 go. So we can basically plot the f1, which is take 1 over square root of 2 here, 1 over square root of 2 here, and when you find that coordinate, you can draw the vector f1. So f1 will be in this direction. You could also draw f2. F2 will be in this direction, right? And this is why they are called the principal axis, because they determine the new coordinate u and the other coordinate v. Right? So I think this makes sense. So we can just extend this and extend this. Okay. So F1 and F2 determine the vectors in the new coordinate system. Now we should the next thing that we need to find is the angle between these two new coordinates. And I think the angle is given. So let's call it theta, which means the angle between the two coordinates. So the old coordinate x and this gives us the angle between the two coordinates, and this is given as the inner product of what? E1 and what? F1, as you can see from the diagram, is the inner product between E1 and F1. Okay, now cos theta is given as that, and then what is E1? I think is 1 0, and F1 we know it is 1 over root 2, 1 over root 2. Now when you find the inner product of this, what does that give us? This basically gives us 1 over root 2, because theta equal to 1 over root 2, which means theta is what? Cos inverse of what? 1 over root 2, which is actually 45 degrees, right? So basically, you can also use the angle to determine how to draw the new coordinate. So this is 45 degrees. Don't draw 45 degrees and extend that line through the origin. That will give us u. And then just plot another 90 degrees from there. You can get your v, because remember, the vectors are orthogonal and orthonormal. If they are orthogonal, that means the angle between them must be 90. So the angle between F1 and F2 is 90 degrees. So now we have this. Beautiful, beautiful. Now we are here so far. What do we do next? It's now time to draw, to sketch the new function. Now, what is this function in itself? U squared plus 9v squared equal to 9. Now, notice we could actually try to understand what we have. U squared plus v squared plus 9v squared equal to 9. So what you try to do is to find, remember we are now in UV coordinate system, you need to find where the function crosses the x-axis and where they cross the y-axis. In this case, where they cross the u axis and where they cross the v axis. So we make v equal to 0, and we get that what? U square must be equal to 9, which means plus or minus 3, right? Now, when u equal to 0, this means that what? 9v square will be equal to 9, which means v square is equal to 1, which means v is equal to plus or minus 1. So these are the coordinates. So plus or minus 3, 0, and this is 0 plus or minus 1. Now let's go back to the function and signify that. So we know that what? When v is 0, x passes through 3 and what? Minus 3. When when u is 0, this function passes through 1 and what? Minus 1, as you can see on the v axis. So therefore, this is actually equation of an ellipse. So it looks like this. So let's say here is the minus 1, okay? Right. So this is the equation of an ellipse, and right, okay. So that is the sketch of the function. Is the function is an ellipse basically that passes through those coordinates, okay? Now, we've been able to sketch the function. We're able to find the angle between the two coordinates. We're also able to find the principal axis, which determines the vectors in the new coordinate system. Now, what is left is we need to know how to convert a vector from one coordinate system to another coordinate system. Basically, if you have a vector in this UV coordinate system, what do they represent in terms of what? XY coordinate system. Okay. Now that's what we'll do to complete this problem. So let's go right ahead and do that. So finally, if we have a vector A in XY coordinates, we said this vector is also equivalent to a vector. This same vector can be written in terms of what? UV coordinates. So what I mean basically is this. Notice that what, for example, F1, right? In terms of UV coordinate is actually, you can see that it is what? 1, 0, right? In terms of UV coordinates. So what I mean is, if you look at F1, in in XY coordinate, we got it as what? 1 over root 2, 1 over root 2. Now, the equivalent of this in UV, this is in XY. In UV coordinate, in terms of this, is going to be 1, 0. This will be the equivalent in what? UV. And you can notice it from here because it's passing through directly in the U axis, right? And this is what we're trying to learn how to convert. Okay. Now, how do we do this? Now, any vector in XY coordinate can be written as what? X times the vectors, the basis for XY coordinate, which is E1 and E2. As a linear combination of what? E1 and E2, we can write this. The same way, any vector in UV coordinates can be written as what? U was what? U of F, U times F1, a linear combination of F1 and what? F2. Now, all we need to do now is to simplify the right-hand side in such a way that what we can compare it to the left-hand side. So how do we simplify that? What is F1? Is 1 over root 2, 1 over root 2. What is the right F2? Minus 1 over root 2, 1 over root 2. Okay, good. So let's focus here on this place a little bit. Now, notice that what F1 can be written in terms of E1 and E2. This is basically 1 over root 2 E1 plus 1 over root 2 E2, right? I think we just discussed this a while ago, right? Any vector this way can be written as what? Linear combination of what? E1 and E2. Okay. Then the same thing here. This is minus 1 over root 2 E1 plus 1 over root 2 E2. Don't forget what E1 and E2 are. 1, 0. E1 is 1, 0. E2 is what? 0, 1. So you'll be able to figure this out, that they're actually the same, right? All right. So now from here, we need to now collect like terms for E1 and collect like terms for E2. So for E1, So the terms that have E1 is U over root 2. And we also have E1 here, which is minus V over root 2. Then we go to E2. We also have U over root 2. And here we have V over root 2. Don't forget V is multiplying each term, okay? So now we have this. So when we compare to the left-hand side, it basically means that what? Our X, so compare, so that means X must be equal to U over root 2 minus V over root 2, which is basically U minus V over root 2. And then for Y, that would give us what? So for Y, that would give us U over root 2 plus V over root 2, which is U plus V over root 2. Now, this completes the problem, okay? So now we know how to convert any vector in UV into a vector in what? XY. Perfect. This is perfect. All right. So in the same way, you could also write this in terms of XY. So I could make U and V subject a formula and try to find U and V in terms of XY. You could also do that, but this is quite enough for this particular problem. So that brings us to the end of this particular learning series. In this video, we basically talked about how to sketch the graph of such function, and we used linear transformation to do this by first of all determining a self-adjoint transformation from the quadratic function, and from there we diagonalize this particular transformation and convert this to a new coordinate system, which helps us to easily draw the graph of the new function that is in terms of uv. So basically that is the whole problem. So thank you very much for staying till the end of the video. I'll be solving a more complicated version of this in the next video. So stay tuned and subscribe to this channel if you haven't done that. Like, comment, share in your social media, in your other platforms, so that other students can benefit from this video. So have a nice day, guys.